Let's look at basic shapes of functions and how they look when we transform them. Y equals 3. How would that look like if you graphed it? You're allowed to pick anything you want for x. And what about y? We know that y is always equal to 3. X can be anything you want. So x could be 1, 2, 3. Can you see that this would be the shape you'd get? 1, 3, 2, 3, 3, 3. Gives you a nice straight line going through 3. Y equals x. I hope you're familiar with that. You've got the point where y equals x, 1, 1, 2, 2, 3, 3. Goes up at 45 degrees, and this shape, please know this one. Because essentially all the other shapes are just transformations of this one. So when you look at y equals x squared, let's start with y equals x. That's a little awful, but you can live with it. When you square these values, what happens to them? They remain positive, but they get bigger. So your graph goes up faster. And when you square negatives, they get positive and go up quicker. And that's why you end up with this shape. Let's use the same logic to draw y equals x cubed. Start with your basic y equals x. When you cube values, they're going to go up a whole lot quicker. And when you cube negatives, they remain negative, but go down faster. That's where this shape comes from. Prediction on x to the fourth. Start with y equals x. Raise these numbers to the fourth power, they're going to get much bigger. Raise negatives to a fourth power, they're going to get positive and bigger. The root of x. Let's apply the same logic. Can you take the square root of a negative number? Not in the reals. So this part of the graph will not exist when we take the square root of x. And when you take a square root of a number, does it get bigger or does it get smaller? That's why we have this sort of shape. 3 more for you. Absolute value of x. So again, start with y equals x. Take the absolute value of a positive, nothing changes. Take the absolute value of a negative, and it simply becomes positive. So that's where the V shape comes from. 1 over x, we've dealt with that for a while, so I'm hoping you recognize this immediately. One way to think about it is when you divide by a large number, you get a small one. When you divide by a small number, you get a large one. Same thing happens with the negatives. Divide by a small number, divide by a big negative, get a small negative. Divide by a small negative, you get a big negative. So that's why that shape works. Look at this shape and see if you can figure out what 1 over x squared looks like. So this time we're looking at 1 over x. Why? Because that's a lot more like 1 over x squared than anything else. When you square these values, the big numbers get bigger faster, the small numbers get smaller faster. What about those ones? They all become positive. So you must know your basic shapes. Other things you should be aware of. The importance of the point 0, 0. It's either on almost every single graph we've drawn, or it's where the asymptotes intersect. So a really important point for almost every graph we've drawn. Can you name another point that's important? How about 1, 1? It's on that graph, and that one, and that one. And if you backtrack, you're going to find it on all the others as well. And that just helps you get a sense of how quickly to make your graphs go up. All right, how do we go about sketching things? When you're looking at a graph like this, the first thing I'd like you to do is get rid of all the extra numbers. If they were not there, we'd be looking at y equals x cubed, which we know. Then start looking at your numbers. What sort of transformation is taking place right here? Shifting right 3. So when we shift right 3, we just pick up that shape and move it to the right 3. Last part of the transformation, what happens when you multiply by 2? So we take our most recent version of the graph, shifted right 3, and when you multiply by 2, the point at 0, 2 times 0, stays at 0, but all the other points, imagine just stretching them up a little bit and pulling these down a little bit faster. And there's our final answer. So we should be able to take our basic shape, shift it right 3, stretch it, and we're done. The other thing I'd like you to look at is the domain and range of this function. So when you're looking for domain, you're asking yourself, is there anything I am not allowed to put in for x? No. So that means whatever value you put in for x, there should be a y value. Whatever value we put in for x, there should be a y. Whatever value we put in for x, there should be a y. So the domain, x is a member of the reals. What about the range? Are all the y values represented on the graph? Certainly looks like it to me. So the range, y is a member of the reals. Let's do another one. Again, your first step, imagine getting rid of all those numbers and seeing what our basic shape is. Y, absolute value of x, we know immediately what it looks like. Then we'll start looking at the numbers. When you look at the numbers, what sort of transformation is happening here and here? We're going to go right 1 and up 4. So that's when we look at that key point at 0, 0, and we move it right 1 and up 4. Fascinating. Okay. So the example I have over here is going 3. So we'll just keep it consistent with what we have over here. So right 1 and up 3. Then let's just examine this new shape, absolute value, right 1 up 3. What happens when you multiply by a negative? Flips it upside down, and the 3 is going to stretch it. So there's our upside down and our stretch. Last thing we want to look for, what is the domain and what is the range? Domain, any restrictions on x? Is there anything we're not allowed to put in here? No, looks like all the x values are represented, so x is a member of the reals. The range, I don't see any y values up here. So the range, we're starting at 3 and it's everything below 3. So y less than or equal to 3. Let's do another one. If we were to take out all sorts of numbers, we'd be looking at the graph y equals the root of x. And we know that shape. And now we're going to start transforming it. Let's start here. 5 minus x. What sort of shift is that? What would make this equal 0? I think 5 would. And what does that negative do? Do you remember it flips it the other way? So the negative flips the graph about this axis, and then we're shifting to 5. Okay, we've got that as our basic shape. Let's do some more transformations. What about the minus 2? That would drop it. If you want to go straight from looking at the original to right here, you're able to do it. You know, you go right 5, down 2, backwards. Last transformation, what happens when you multiply by a half? Doesn't move the vertex or the key point, it just shifts everything down. So all these points are going up half as much as they used to. All right, domain. Well, we've got some restrictions on this, don't we? We're defined, we have points on our graph all the way up until 5. So for our domain, we should have x less than or equal to 5. And our range, got all kinds of y values. This is going to go up and up and up and up, but it starts at -2. So our range, we would have y greater than or equal to -2. Okay, your job today, there's lots of graphs for you to do. The not Q depends on how far you've gotten in your 12A class, whether you know how to graph it or not. But our goal is in the space of about 10 seconds that you draw a reasonably accurate graph. Start with the basic shape, move it left, right, up and down, and then scale it if you have to. All right, get lots of practice at this. You need to be good at this. Have fun.